Now let us continue with the proof of the Picard-Lindelöf theorem. The reason I did not explain the proof in the lecture is because this is a complicated proof. It has a lot of steps, and I strongly believe that the best way to understand a proof is to construct it. So that's why rather than me doing all the work, I gave it to you as a series of exercises. So let me go through the ideas behind the proof. Now, the first step of the proof of the Picard-Lindelöf theorem is to change the initial value problem from an arbitrary point to the origin. So geometrically, it means the following thing. It means that we take exactly the same vector field, but we change the coordinate axis, right? So if initially we had this was the t-axis and this was the y-axis, then what we are going to do is we are just going to introduce new coordinate axis. So this is going to be the new y, and this is going to be the new t, and we are going to call this psi and this tau, just Greek letters. Now it came a bit of a surprise to me that it was this step that I need to explain again, because in my group everyone has solved this question correctly and they didn't have a problem with it. But anyway, since a lot of you requested for it, I think there were like 50 requests, so I'm going to explain it nevertheless. So here is what's going on here. So we are going to make a substitution in this differential equation, and the substitution is just like this. So geometrically it means we are moving the coordinate axis so that the origin is at the given point. So it means that tau, our new variable tau, is t minus t0. So now imagine that when t is equal to t0, tau is going to be t0 minus t0 is 0. So tau 0 is 0. Now psi is going to be y minus y0. So it means that the initial value of psi is going to be y0 minus y0, 0. Right? So at the same time, notice that we can move t0 to the right hand side, to the left hand side, and y0 to the left hand side. So t is tau plus t0, and y equals psi plus y0. So furthermore, let us transform the differential equation. So the left hand side is y prime, or dy dt. So what is dy dt? By the chain rule, dy dt equals dy d psi times d psi d tau times d tau dt. Right? That's just the chain rule. So it's sort of the chain rule tells us that when you're using this notation, then these differential sort of cancel out. It's not true cancellation, but they behave in the same way as if they were fractions. Right? So this is the chain rule, familiar, hopefully from the secondary school, but we can apply it here too. Well, dy d psi, so y is psi plus something. This is a constant. When you differentiate y with respect to psi, it's just 1. So this is just 1. And this is also just 1, right? Tau, the derivative of tau with respect to t is just 1. So this is 1 times this, so this is just the psi d tau. So which means our differential equation, the left hand side is dy dt, it becomes d psi d tau, and the right hand side is f of, well, t is tau plus t0, and y is psi plus y0. And the initial condition, so as I said here, is changed to psi of 0 is 0. Now, why are we doing this? Is because now an arbitrary initial condition is transformed to the initial condition at 0. So the initial point can be transformed to the origin. Well, and as you will see in the next step, it just helps us to simplify the process. Currently, let me just give you maybe one specific example. So let's say that we have the differential equation y prime equals t minus 2 times cosine y. All right, and the initial condition is y of 2 equals 1. So by introducing these new variables, tau equals t minus t0. T0 is 2. And y equals, psi equals y minus 1. So from here we know that t equals tau plus 2 and y equals psi plus 1. Now we can transform our differential equation. So the left hand side, as I said, becomes just d psi d tau, and the right hand side is t is tau plus 2 minus 2 is just tau times cosine, and y is psi plus 1, psi plus 1, and psi of 0 is 0. Okay, so now our initial value problem, this is equivalent to this initial value problem, in the sense that if we solve this initial value problem, then of course we can always, if we know that if we solve it and we know that psi is some function of tau, then y is going to be psi of tau minus plus 1, and t here is going to be tau plus 2. Sorry, the vice versa. Tau is t minus 2. So it's t minus 2 plus 1. Right? So which means that hypothetically, if we solve the initial value problem for psi, it's going to be some function of tau. Then to get the solution for y, we're going to let tau be t minus 2, and then we do plus 1 to the whole thing, and that's going to be the answer for y. And of course vice versa, so we can change one to the other, and back these two initial value problems are just equivalent.